Okay, so let me introduce our first speaker. This first speaker is a great friend of mine, and many people who have been on JPrime 2015 actually know that he was our first speaker at our first JPrime 2015. So it's a really good tradition for us to start like every 10 years
Exactly.
with our great speaker, Heinz Kabutz, who make his way from Crete to actually open the JPrime 2025. Heinz, so happy that you're here, and great. And please welcome Heinz Kabutz.
Thank you so much. It's an absolute pleasure to be back. And I remember the first JPrime. I actually forgot about it because I just remember this place, this particular location. And I remember we were in another location somewhere else. And I met Ivan. And the first time I met him, he was walking at about, I don't know, 9 o'clock in the morning, carrying a beer. And I thought, this is definitely going to be a very different type of conference. And this is just a fantastic place. So I love coming to JPrime. I've missed a few sessions, a few editions, unfortunately. What's interesting is that the very first talk I gave 10 years ago was about concurrency. And now we again have a talk about concurrency, the hidden art of thread-safe programming. And we're going to look at the java.util.concurrent package. So what often happens is it's really hard when you're doing a talk to get the timing right. And quite often at the end, we're a bit rushed. So what I'm going to do a bit differently today, I'm going to start with questions. All right? So here's your chance to ask some questions about java.util.concurrent that you've always wanted to ask. We've got space for 3 questions. Let's have them. Come on. Don't be shy. So we're doing the QA at the beginning rather than at the end. So is the slide a race condition? No, it's not a race condition. Out of order slides. That's actually a great idea, but then that's not a question for java.util.concurrent. Don't be shy. Go on, ask. Anything about java.util.concurrent that you've wanted to ask? We can't continue until we've got some questions. So, oh, there's a hand. Excellent question. How do you get good at concurrency? And that's a really, really great question. How do you get good at concurrency? Great question. It's a fantastic. I've got a great answer for that. Let's hear another question. That was a fantastic question. Yes, sir. Sorry, I didn't quite hear that.
What are the milestones we need to keep in mind when we're designing a concurrent?
Okay, what are the milestones? I'm going to reword that a little bit. What are the milestones? Okay, I'll just put it down. We need to keep in mind when designing an application. Okay? Third question. Oh, that's a great question. Thank you. Okay. Is structured concurrency the silver bullet? All right. So I'm going to answer the second question first. What are the milestones we need to keep in mind? because I'm not sure I understand the question correctly, so I'm going to reword it a bit. It's basically what I think you're trying to ask is, what do we need to consider about concurrency when designing our application? Right? So basically, anywhere where there's something which is accessed by multiple threads, which is quite often, any data, and this is all about data, not about programs as such, it's actually shared data. Whenever we have shared data, we need to either make sure that data is synchronized correctly, not necessarily the synchronized keyword, but generally, or it must be immutable, or it must be unshared. And if we follow those principles, it really helps us to really helps us to get an application which is thread safe. All right. The first question, which I really like a lot, I'm going to answer in the middle of the talk, and the last one at the end of the talk. All right. So I'm going to start by looking at a class called java.util.Vector. Who knows Vector? Okay, actually some of you. Now that's a very old version of ArrayList, which is a thread-safe version of ArrayList. It is synchronized. Most methods are synchronized. And the way it was in the version 1.0, because this is a very, very old class, they had all the methods which changed vector, which did a write operation. All those methods were synchronized. And the methods which were not write methods were not synchronized. So there actually were concurrency bugs in version 1.0 of vector. This is what it looked like. We had a protected int element count. We had a public final int size, which returned the element count. Now, the element count is a field, and remember, with concurrency, we're talking about shared data. That's what we're worried about, to make sure that that is thread safe. And there's a synchronized add element, which prevents race conditions on the change, but the problem is that size could return stale values. So what could happen is that I read the size, but I'm seeing the size of what it used to be, not what it actually is at the moment. In Java 1.1, they introduced a race condition into vector. Now, this is a kind of a weird one, because you look at it and you go, where's the race condition? All they did was they added implement serializable. But that actually causes a race condition, because what happens now is that they if I'm writing a vector into an output stream, at the same time as I can change it, then I'm going to get a vector output that's mangled with incorrect data. In Java 1.4, they fixed both problems. First of all, they made also the read method synchronized. So you have, for example, the size being synchronized. But also they made the write object synchronized. So they fixed both problems. That's Java 1.4. All right? 1.5, oh, sorry, actually, in 1.4, so when they made so what they did, let me just double check, just show this again. They added a write object method, which then writes to the object output stream, making that synchronized, meaning that you can't write to the object output stream whilst you're busy changing the vector. But that introduced a very, very strange type of deadlock, because if you've got vector 1, which points to vector 2, and vector 2 points to vector 1, and you write vector 1 and vector 2 with two different threads at the same time, you could get a deadlock. And I wrote about this years ago. This was still Java 1.6 when I wrote about it. And I said, there's no ways anybody would ever do this. Nobody would ever have a vector point to another vector and then write them both at the same time. But it turns out somebody actually did this and logged a bug, and IBM fixed it, and that fix went into Java 1.7. So this is now the 1.7 version. We can see that write object has been changed. We first make a put fields. We then put the elements, we clone the element data, we make a clone of the array, and then we write the fields without holding the lock. So we do the actual write fields without holding the lock. And this prevents the deadlock. The deadlock happens when you first get one lock and then the other lock, and then the other time you get it in the opposite order. So that gives you the deadlock. So all's good, right? Well, no, because in Java 1.8, they introduced for each. And for each does the following. We're iterating, it's synchronized, we're iterating over the collection, and we're calling action.accept element data. So it's very easy to cause a deadlock in Java 8. Because what you can do is you can say for each, and then all you have to do is say contains in another vector, and do the same thing in the other vector, and again you get the same situation where you are first getting the one synchronized lock and then the other synchronized lock, and you end up with a deadlock. And then there are other deadlocks as well. For example, if you say vector1 equals vector2 from one thread, and at the same time vector2 equals vector1, then again you can get a deadlock. But so what can we learn from this? We learn from this that there are lots of very strange edge conditions that could cause a deadlock. Deadlocks normally are not such a problem, because if you get a deadlock, you will see your deadlock in your stack trace. And at the moment, you can only see them for platform threads. In the future, we'll probably see them for virtual threads as well. But for now, you just see them for platform threads. The other thing is that we don't always see these bugs when we do tests, because our tests don't expose the concurrency bugs unless we're looking for them specifically. Some of them are really, really hard to find. You need to know what to look for. So I started a couple of years ago writing courses which nobody will ever want to buy. You might wonder, why would I write courses nobody ever want to buy? Because I really wanted to dig into java.util.concurrent in a level that no one's ever done before, right? And so this is what I started here, and that's actually what I'm talking about here as well. You see, writing correct thread-safe code is a challenge, and this answers already the second question to some extent. You see, we've got a rule book. We've got the law, the Java memory model. And the Java memory model describes how threads must communicate between each other. It has rules for happens before, in which order things must happen, access safety. But the problem is you don't know whether a class adheres to the memory model 100%. There's no test. There's no way of taking your class, putting it into a test and say, right, our code now complies 100%. So we have to run our code and hope it works correctly. And some bugs are extremely hard to detect, and this is what makes it so hard. Normally, when you write some calculation, you can run it through the test and see if the answer is correct. But here we can't, because here we run the test, we don't actually know whether our code is correct if the test passes. It's a bit like driving laws in Bulgaria, right? And Greece. So, all right. So here's a very interesting bug that I saw in the bug database. There's a very rare situation on lock support. There's a class called lock support, and somebody at Google discovered that sometimes the threads wouldn't get unparked. And so he wrote a test, a really smart guy, wrote a test, let it run for a whole week, and a whole week of CPU time, he managed to get it to cause this problem. So it's like running it over and over and over again, thousands, millions of virtual machines starting up and so on, until eventually he found a situation where the thread would not unpark itself. And extremely hard to discover and diagnose. And so the recommended workaround was to do the following. In any class that uses lock support, so if you use lock support inside your class, you would say static, and then you'd load the class, you'd say ensure loaded lock support.class. And you'll find this in a whole bunch of different classes, like, for example, concurrent hash map. Anywhere where you see lock support being used, almost anywhere, they have this weird code snippet. So what I did was I searched through and I found there are a few places where they don't have this, but this is all new code. So I don't know whether this is a problem or not. I don't know today. It was a problem in Java 7. I'm not sure it was a problem in Java 8. I don't think it's a problem in Java 9. But if you said to me, here's a gun against your head, is it a problem? I would say, I don't know. Right? And the funny thing is I logged a bug against the class which didn't have this. And the people who really know this stuff, they're also not sure. So nobody really knows. And unfortunately, this is really tricky. So one of the reasons I started on this path down of really studying in great depth java.util.concurrent is in Brian Goetz's book, Java Concurrency in Practice, he basically says that don't write your own synchronizing classes. Use what's in the java.util.concurrent. So I thought to myself, well, what magic do they have that's different to our magic? Like, are they that much cleverer than us? I mean, probably, but and I'll explain to you now why this is useful to study. First of all, by studying it, you learn what is available, but you also learn how to write robust thread-safe classes. I found a whole bunch of bugs in java.util.concurrent classes by studying existing classes. So I found bugs in other classes by studying existing classes. All right. Now, good versus bad code. We all make mistakes. Everybody makes mistakes. In German, there's a saying, Vertrauen ist gut, Kontrolle ist besser. It's good to trust, but it's better to check up on it. You know? And that's where we have this test-driven development, unit testing, and so on. That's really important in order to make thread-safe code. And it's also best to rely on well-known, well-used synchronizers. So, for example, if I need to choose between concurrent hash map and concurrent skip list map, I would rather use concurrent hash map because it's more used. Right? If I need to choose LinkedBlockingQueue, LinkedBlockingDeck, I'd rather use LinkedBlockingQueue because it's more used. So you always take the class which is most used. And anybody can report a bug on Java code. And I've reported quite a few, especially recently. And these are, I did one in link transfer queue quite a while ago, and then one in concurrent skip list map. Since about Java 10, concurrent skip list map hasn't been doing parallel streams. You think it is, but it's not. And it's been like this for ages. Nobody noticed it. And then one in ArrayBlockingQueue, and then 5 in LinkedBlockingDeck. Right? Now what I've done is I've now bundled them all into one bug, so hopefully in a month or so that's going to get all fixed. But I've never used LinkedBlockingDeck in my own code. I was looking at LinkedBlockingDeck to use for my course, for the teardown course. But I've never used it in my own code. I've used LinkedBlockingQueue quite a lot, and I've not found a single bug in LinkedBlockingQueue and looked at it very, very in great detail. How many of you have used LinkedBlockingDeck? Right, okay, I think. Concurrent hash map, anybody? Right, there we go. That's exactly my point. So if you look in the JDK, concurrent hash map is used hundreds of times. And then you've got CopyOnWriteArrayList, concurrent linked queue, concurrent linked deck, future task, and LinkedBlockingQueue, and these are used quite a few times. And then the rest is not used very much. So my suggestion is use the ones which others use a lot. And you'll have a smaller chance of there being bugs. Not zero, but less. So use the most used ones because that's where probably the least bugs are, because others have found them for you. And that's also the reason why we don't want to write our own synchronizers. Because if we write it, if I say, you know, somebody's written, I don't know, some clever synchronized, I don't know, sorted list, and nobody's heard of that, Nobody's used it, so therefore you have a high chance of bugs. Oh, something. This is for a free gift, a course. If you want to take a picture of that, you'll get a free data structures course. I tried to make it as big as possible so you can all see it. Hopefully it'll work. And hopefully the internet, this is actually a test of the internet to see if the network works. Now if you missed that, it's tinyurl.com/jprime-25. Write that down. And that's going to expire this evening. So make sure to get it before this evening, otherwise it won't work. tinyurl.com/jprime-25. All right. So let's look at something else, which is striped 64. So what I want to try is to increment a number 100 million times and see how quickly that happens. So let's go to here. We write some code. We're going to say int stream.range 0,100 million. We're going to say .parallel. And then for each, we're going to let's start with atomic long var atomic equals new atomic long. I was traveling to Israel once, and I had this long interrogation, why am I going there? And they said to me, why are you going? And I was going to teach Intel, do some training for Intel. And they said, can you show us the course? And I opened the course, and it was on the slide about atomic integer. And I said, let me just go to the beginning of my talk. So here we can see, if I run this atomic integer, atomic long, 100 million times, see how long it takes to complete, 5.4 seconds. Right? So it runs for quite a while to finish, 5.4 seconds. If I do the same thing with the LongAdder, and I say again int stream.range from 0 to 100 million in parallel, and I say add an increment, and I put again a timer around that. It's going to be the adder time. We see how long that takes. So the other one took 5.5 seconds. And this, less than 100 milliseconds. So you can see a massive difference between the two. One takes 5.5 seconds, the other one takes 100 milliseconds. So what I want to look at here is, how does it actually work? How does it run so quickly when the other one takes a long time? And so let's have a look at this magic. And if you look at LongAdder, LongAdder extends a class called striped 64. And it uses something called lock striping. Instead of having a single shared variable, we have multiple shared variables, which we then merge when necessary. So when you say long value at the end to get the sum, it's going to add up all the values. But what happens with striped 64 is when you construct the first LongAdder, it stores the value inside a transient volatile long base. So you've got a volatile long base over here, and that's just a 64-bit value. So what happens is if you do a compare and swap, and you lose the race, then what happens is that they expand that to be an array of cells. And they basically spread the cells assign the threads between the cells using it's like a pretty weird randomizing function to try and reduce the probability that two threads go to exactly the same cell. So that's how they do it. And that information is actually stored in the thread itself. All right, so you've got your cell over here. The cell is contended. What contended means is that they make the object bigger so that it lives by itself in its own cache line. Mustn't forget that there's always memory running underneath, which is in hardware, which is running our code. And if we have multiple cells sitting in the same cache line, and you update the one, they both have to be flushed out to main memory. So by having it contended, each cell will always live by itself in a cache line, will never share with anybody else. You don't get false sharing or true sharing. All right. So that's how it works. And so what happens is the first time that you get a conflict, it will create a cell array of size 2. If you get another conflict, it's going to double it again to 4. If you get another conflict, it's going to double it to 8. And it's going to keep on doubling it until you get to an array which is not greater than the number of hardware threads in your system. So I've got 12 threads in 12 cores in my machine, my laptop. So it's going to go up until, so not bigger than to the power of. So it'll go up to 16. It won't go beyond 16 threads. So it doesn't matter how many threads I have, concurrently updating it, it's never going to go to more than 16 cells. But they distribute amongst the threads so that you have a fairly good distribution of the threads to the cells. You don't have all threads going to a single cell, for example. That's how it works. So it's really amazing. And the LongAdder basically uses this and also the long accumulator as well. So the best way to deal with contention is to not have contention. It's to reduce the amount of contention. Contention is a real performance killer. And you'll see this in lots of different cases. All right, let's look at something else. So let's say that we've got a service that takes some time to get started. And other parts of the code are depending on the service. So what we want to do is we want to wait for that service to start, but we don't want to worry about things like interrupted exceptions everywhere. You know, those are a pain. Nobody likes interrupted exceptions. So what we're going to do is we want to look at different ways to do this, and also avoiding having to worry about catching interrupted exception. So I define an interface called starting gun, and I've got two methods of wait uninterruptedly and ready. So the threads, which are the parts of the code that are waiting for the service to start, we'll call await uninterruptedly, and the one that starts the service will say ready once it's done. All right. So I'm going to show you 3 approaches, and this actually answers the first question also a bit. How do you get good at this? The first one is doing it just from first principles. And here I've got a starting gun monitor, implement starting gun. And the reason I call it monitor is that it's using synchronized, and synchronized is also called monitor locks. So here's my, I've got a field called ready, Boolean ready equals false. I've got a method called await uninterruptedly, which is synchronized. And I first of all start by saying interrupted. I remember what the status of interrupted equals thread.interrupted. And then I say while not ready. So what thread interrupted does, it also resets the state to no longer be interrupted. So it's like you remember it, but you don't keep it interrupted. I then say while not ready, I try and wait. It needs to be a while loop. So you wait, keep on waiting. If you get interrupted, you get an interrupted exception, you'll simply remember that. You say interrupted equals true, and then you'll continue waiting until you exit normally from the wait, and you are ready. Now the wait is problematic. The wait is not fully compatible with virtual threads. So it will work to some extent with virtual threads, but not entirely. All right? So we need to be a bit careful with that. And once we are ready, we go here, if interrupted, thread.current thread.interrupt. Okay, so we reinterrupt ourselves, and we exit from there. And the ready will simply say ready equals true. It's a synchronized method, and notify all, which wakes up all the threads to now continue. So this is, as far as I know, is thread safe. I believe this is correct. I had a talk in Germany and somebody complained about something, but I think they're wrong. I think this is actually correct. But you see, it's very low level, and it does have a problem with virtual threads prior to Java 24. Let's look at another way of doing this. We could also do it like this. We could say, let's simply use countdown latch, which is similar to what I want to do, but what we'll do is we will catch interrupted exception and just sort of ignore it temporarily until we exit from there, and then we reinterrupt the solve when we exit. So the code's almost exactly the same, but I don't have to worry about synchronized. I've got something which is compatible with the fork join pool. It's compatible with virtual threads. So it's like a little bit better approach to doing it. Right. Now the third approach, first of all, the first one has a bit of a problem. As I said, virtual threads don't work too well, and it's quite hard to do that. But both times I have to catch the interrupted exception, and it actually make the exception itself, which is we're still paying the cost of creating the exception. So another approach would be to use exactly the same as countdown latch. So here's what we do: is we go to we take countdown latch and we do a copy and paste of the inside. Now, normally you're not allowed to copy and paste code from the JDK, but this is one exception. The java.util.concurrent libraries actually are in the public domain. So we're going to copy and paste it here, and I'm going to. I just need a few of the class, not all of them. So basically, I need this abstract queued synchronizer. The int count is always going to be 1. So I can just say set state 1. I don't actually need this. I can do it like that. I don't need the int count, getting the count, because it's always going to be 1 or 0. I could have an isReady. I'm going to here simply say equals new sync. That's the sync. Delete this, don't need that. Await is going to be almost exactly the same, but it's going to be await uninterruptedly. And so here, I'm relying on the abstract queued synchronizer, and here I'm going to say acquire shared rather than acquired shared interruptedly. And that does all of the code that I wrote for me in one line. So that's the same as what we saw over here, all of this await uninterruptedly, except we're not actually generating an interrupted exception. It's saving it for later, and so that's all I need to do. Await acquire shared, and then ready would be the same as, let's delete this, I don't need that. I'm not going to use a timed await. That's going to be the same as countdown. So ready will be release shared 1. And the rest I think I don't need. I don't need the get count. I can delete that. I'll delete the toString as well. So this is my code. It simply is going to be let's put this up here. It's simply using the countdown latch, but simplified, using the same code. Copy and paste of the code. All right, let's double check that it's correct. So I've got a test for that. Starting gun, this one over here. And hopefully I didn't make a mistake. And I don't think I made a mistake, but you know, these things are hard to test. So these are the different ways of doing it. Which one's best? Well, sort of in a way, the best is the last one, but it's a lot more work. And I think that the second one might be better, because I'm relying on a class that is in the JDK, the countdown latch, and if there's a mistake there, then we can fix it there, and it's fixed for everybody. All right, let's look at something else, the LinkedBlockingQueue. This is quite a fun one. So the LinkedBlockingQueue has a design, it's like a linked list, but it has 2 locks, one for putting and one for taking. One to put something in, one to take something out. And so this means that I can have 2 threads putting and taking at precisely the same time. if I've got a single producer, single consumer case, you typically have higher throughput on this than on a queue which has a single lock. But it can be quite interesting if you've got a single producer and multiple consumers. Because what happens is you've got a single producer putting elements in without any contention, being able to put it in very quickly, but at the front of the queue, you've got the multiple consumers fighting over the lock to take elements out. And the queue gets longer and longer and longer, and you get lots of full GCs whilst it's trying to clean everything up. The interesting thing, though, is because you've got two locks, you've got the put lock and the take lock, you cannot rely on visibility with the locks because they've got different locks. So the way they do this is they've got an atomic integer for the count, and they piggyback off the atomic integer in order to make sure that you're seeing the changes made by the other on the other lock. So let's have a quick look at this demo as well. So I'm going to make a test method here, pass and linked blocking queue, and no, that's wrong. Let's create a method here, and that's going to be just a blocking queue of queue, and we'll call it integer. Okay, and then we're going to go comma 1. That's going to be the 1 is going to be the number of consumers. So that's going to be the number of consumers. So we're going to start with 1. So we're going to have over here pretty much what I want to do. Var pool equals executors.new cached thread pool. Then I'm going to say thread.offPlatform. I don't know, pool.submit, sorry. And it's going to be over here. I'm going to say 0 up to 10 million. And I'm going to say put into the queue the value of 42. I'm going to have the same value so that you don't have to make objects for the integers. And then once I'm done with that, I'm going to say 0, it's going to be the consumers up to the number of consumers, and we're going to make pool submit. This is going to be 10 million divided by the number of consumers, and we're going to say q.take. Right? Luckily, IntelliJ has seen me do this before, so the AI has sort of remembered my previous demo. So we print out the time, and we also print out the q.getClass. Let's run this code, and we see the link blocking queue took like a second to do this work. And let's do this a few times, 0 to 10, so we don't just do it once, do it a few times, and we'll see how well we performs on the link blocking queue. So it's sometimes it does better than other times, and one of the reasons is that sometimes it's doing a GC whilst it's running the test. So let's do a system GC at the end. You would never do this in real code, but in the test it's okay to do this, so that we can clear it and hopefully get more consistent results. So you're looking at about 750, 800 milliseconds per data point for the link blocking queue. Right? Let's try the link blocking deck now. Now the link blocking deck is a bit different because it has a single lock that it uses for put and take. Because you can add in at both ends of the queue, they can only do it with a single lock. And if you run the code now, you can see that it performs a little bit worse than the link blocking. Oh, that one was better actually. But most of the time it performs a bit worse than the link blocking queue. Right? Let's take the array blocking queue, which also has a single lock. Let's give it 10,000 elements, that should be enough. Array blocking queue. And again, it's okay, it's about a second. But it's not as good as the LinkedBlockingQueue, which was consistently about 750, 800 milliseconds. All right, now let's try this one with 2 threads. And now the 2 threads, whoa, look at that, that's nice and fast. Amazing. Let's try the link blocking deck with 2 threads. Pretty good. All right. And let's try the link blocking queue with 2 threads on the consuming. Oop. And it's actually gotten worse. It's a bit like link blocking deck at the beginning. And this can happen. You see, this link blocking queue is used by the fixed thread pool. So if you have, for example, a fixed thread pool of size 1 thread in there, and you give it a bunch of jobs to do, short jobs, it's going to be able to pull them out very quickly without contention, because it's one consumer. But the moment you have 2 threads inside your fixed thread pool, those 2 threads are fighting over the lock for take. And so they have massive contention on there. And so you end up with it actually being slower than with a single thread. Here's another fun one, the ArrayBlockingQueue. This does weekly consistent iteration. And so, for example, if you have a queue and you've got 1, 2, 3, 4, 5 in there, and you make an iterator, you get the first 3 items, and you then add another 5 items to that. You then end up, if you keep on iterating, you see the rest of the items. If you try to do this with an array deck or an array list, you'd get a concurrent modification exception. But because this is thread safe, it actually works. So, but there's a problem with ArrayBlockingQueue in that it's basically an array that's a fixed size, and if you keep on adding and taking elements, it's going to go wrap around the array, right? And so behavior is going to be slightly different to how linked blocking queue iteration would work. However, what's interesting here is that you basically somehow ArrayBlockingQueue needs to notify its current iterators that it's wrapped around. So the moment it wraps around, it notifies more. But there you've got a problem, because if ArrayBlockingQueue kept all of its iterators alive, that would cause a memory leak. So what they do is they use weak references to point to the iterators in order to keep them sort of alive, as long as they still have some elements inside. Right. I want to quickly show you this one other thing. I don't have that much time left. And that's the double-check locking on the CopyOnWriteArrayList. So the CopyOnWriteArrayList is fairly simple class, but here it gets interesting, because what they try and do is they've got a couple of places where they really try to avoid getting the lock and doing something. So if you remove an item from the CopyOnWriteArrayList, the remove object is an order n operation. So if you've got a very large CopyOnWriteArrayList, it's going to take as many steps possibly to find whether the object's there or not. So what they do is they first run through the array to check whether the item is there or not. So it iterates through it, looks for it, and only once it's found the object does it call another remove method, which then actually goes and removes the item. Now, I'm going to show you some code that you probably have not seen before. I'm going to take a guess here. I hope not. Right. So here's the code, and you click on that, and look at this. Did you know that you can put a label on an if statement? Right? You can we all know you can put a label on a for loop, but you can also put a label on an if statement. So if the snapshot is not the current one, in other words, the snapshot has changed, they then put a label here. Now, I've never written code like this myself, Now, don't take a photo and use that in your own code. This is not my code. This is CopyOnWriteArrayList. And when you look at the code in java.util.Concurrent, it's very specifically written in a certain way. And what they're trying to do is they're trying to minimize the number of bytecodes, and they're trying to write the bytecodes in such a way that the just-in-time compiler and hotspot profiler can optimize them optimally. Right? So this way you don't have very much duplication of the code. And I took this code and I refactored it, I wrote it differently, and whichever way I wrote it differently, it always was easier to understand, but it all resulted in code that wasn't as optimal. So you'll find this quite often in the concurrent libraries, where they've got some horrific code that's hard to understand, or you have to really think about it to understand it, but there's a reason behind it. Right? And that's again a reason why we shouldn't write our own, rather use what's there. So we've come to the end. Unfortunately, as I mentioned, I'm going to GeekOn in Krakow, and I accepted their invitation first because they invited me first, and so I have to leave sort of lunchtime. So if you'd like to chat to me, I won't bite. Don't worry. I love the Bulgarians. And so I'm really, really happy to be here. Please speak to me after this. I'm very happy to chat. If you're not on my newsletter, you should sign up. It's javaspecialists.eu. Don't forget, if you haven't got this yet, grab that. We've got another 1 minute for a question, if there are any last questions. Oh, there's a question about structured concurrency. Thanks. Let's answer that as well. So structured concurrency is absolutely fantastic for describing most of the complex workflows that we need to do. So if you're working with virtual threads, which I really recommend you do if you work with concurrency, then structured concurrency is the way to go. Unfortunately, it's not fully baked yet, and I'm not quite sure why they're taking so long to complete the structured concurrency. I think they want to make it sure it's 100% correct. So I would recommend that if you're doing virtual threads, that you do it with structured concurrency, even though it's still on preview. Because with that, it makes it so much easier to write your concurrent code correctly. And that's all we've got time for today. Thank you very, very much for joining. And I'll be here until 12 o'clock.